all of data.
All right, but let's, this is not G, we are F. We got F. I think we're F. Yeah, this is it.
When you were speaking about the long code, you were speaking of like everything following like the C line, and like you closing like you making symbols invisible, all that stuff following the programming for the most part, right?
Yeah, some of it is more important than others, but,
Huge, justifying like how large you want
the
like,
codes?
or everything like that, yeah.
No, I mean, in this paper, it literally says, these are preliminary, right? I think it says that. So use data, didn't it say something like that? Because I know we're gonna get to the more important stuff, and we'll look at that. So I'm trying not to get you to spend too much time, although, you know, you wanna make things look decent, as decent as possible. All right, that's not the number, so I think we can do this. And let's see.
Yeah, I hope. You're good, thank you.
This screen's tiny. I mean, it seems tiny relative to, you guys had a class in the International Hall yet? The International Hall that's across the,
We had the orientation then.
this screen's way bigger than this one, which helps. All right, so let's just run regress ln total. All right, so there's a regression. There's a log regression. And we know the coefficient on, shall we do below? Shall we do the first one? All right. So there is a growth rate for Merlot for the entire period. 9%. What does that represent? It represents the average growth rate before and after. So even if there was, even if there was some change, we're not accounting for it. So even if this is the true growth, this is the true representation, what does this model represent? What does that equation represent? No, just by itself, the one we just ran right now. So ignore all the other stuff. Yeah, for the entire period, right? So I'm ignoring this event right here. This is literally the equation of a straight line. So it would be like an average, so we'd be estimating, right, a line that looks like that. It ignores the fact that there was some event that occurred. And we get some average growth rate. But we specifically want to answer a question, which is, did the growth rate change? So we need to allow for that change in the growth rate. So this is the right, this is right. This is the average growth rate for the entire period. The problem is we specified the wrong model. And the way to do that is to add the dummy and the interaction. The dummy and interaction really looks at the, it boils down to the equation of two different models, right? This one and that. All right. So we just need to know what to ask Stata, and we'll get the right answer. So Stata's always going to give us the right answer. We just have to know what to ask. So we want to analyze the before and after growth rates. So we specify the full model of it, which is, we include the dummy variable, and think of dummies as shifters. Remember, we use dummies for seasonality, to shift up the growth rates, or to shift up our benchmark during specific months. And that's exactly what it did. It allowed our regression to match the data. Otherwise, go back. So we had data with all this full seasonality. And when we regress the average, just the simple straight line, we got the average growth rate. And that was fine if we're looking for the average growth rate. But when we wanted a benchmark to account for all these peaks and valleys, we added dummies so that that line would shift up there, shift down there, shift up there. And then we got a model that pretty accurately reflected that seasonality. And that was that benchmark model that we constructed. So dummies are always shifters. The first shifter says is a constant. So let's, this should all be in the PowerPoint. PowerPoint's writing is probably better than mine. All right, so we got that. All right, so we got the dummy variable to indicate a shift in the intercept. And then we had the interaction to account for a shift in the slope. And before the event, we get that time trend represented by that equation. After the event is the full model. We put ones where they belong. After's a dummy, it just indicates, yes, I'm after it. And then we collect terms. And we get that. And graphically, that's our before, intercept, and slope. And that's our after, intercept, and slope. And as we said, beta 2 represents the difference in intercepts relative to before. And beta 3 represents the difference in slopes relative to before. But as you can see, it really is two separate lines. One's going that way, one's going that way. So let's run this model real quick. Any questions? All right, so let's put in that dummy. Did you have to construct the dummies or did I?
Your screen is on.
All right, let's see if that works. There's our dummy. There's our interaction. There are our results. Coefficient on time, beta 1, looks like it's 8%. So the growth before the event was 8%. Let's see, the dummy variable is positive. And statistically significant. Remember, we're not looking at a positive event, we're actually looking at a negative event. Does a positive coefficient make sense? Does a positive dummy coefficient make sense? You got a 50-50 chance.
Yeah, it's not going down.
It makes sense if what is true?
Yeah, more growth, positive growth, right? Negative growth would go down.
Or, no, I'm asking you about the dummy variable. The coefficient on the dummy variable, D2005. Does a positive coefficient make sense? And if it makes sense if what is true?
It makes sense it's positive because the growth rate did go down.
Yeah.
If this slope and the first,
If that's true, then where's the intercept of this?
due to the positive variable.
Dummies are shifters. It's gotta be above. This is positive, this is beta 1. And now this is beta 1 plus beta 3. But the main point I want to make is beta 1 minus beta, is that 2? Is that positive coefficient makes sense? It makes sense if that line either flattens or goes negative. And I made it go negative because I wanted to emphasize the fact that it's going to shift that intercept up if that changes, right? So it just makes sense visually. And it makes even more sense when we see what? The coefficient on the interaction term. Because that's the difference in the slopes. Now in this case, we had 8% growth before, and it looks like we're getting not 8% growth afterwards. Yeah, not negative 8% afterwards. Because what does this coefficient represent? What does beta 3 represent?
The difference.
It's the difference in the
Yeah.
slope.
So you would take the first slope and then subtract that second number, and what is left of it is the slope of the new.
Correct. So I'm not a math wizard, but it looks like 8 minus 8 is roughly 0. Yeah.
Maybe it's up like 0.5%.
Yeah, no, we can do that. And this is why it's good to outreg these things, because we could just put a cell and this minus that.
You know, when you were talking interaction,
Yeah.
what number are you looking at there? When you say, so I understand the dummy variables and the shifts
Okay.
that you're talking about, but then you keep throwing the statement in, let's look at the interactions. What number is that? What-
Well, if you know what time is, and you know what the dummy variable
Uh-huh.
is, then there's really not a whole lot left. So what does it have to be? It's, well, you got one of two shots. And we know what the constant is, right? So if you know the dummy variable and time, and you know the constant, then there's only one number left. And that's what?
That's that interaction.
That's the interaction, exactly. And we're really, and interaction is a good term because we're literally saying that time and the event interacted to cause some change in, oops, I think I got two negatives in there. Yeah, that's a really, really small growth rate. It's a really small font showing a really small growth rate. If we had a bigger font, if we had a bigger growth rate, but it's 0.05%. It's less than 1/2 of 1%. 0.5%. It's less than 1/10 of 1%. It's really small.
Half of it is
Which tells us what? That line is probably, I kind of exaggerated this a bit for effect, but we know that the line is essentially what? It's essentially flat. Yeah, it has a slope of 0. So it looks like that. But even then, we know that beta 2 is going to be positive because it's going to shift that line up. And essentially, let me draw a slope of we know that beta 1 plus beta 3 is essentially 0. The slope of this line they cancel each other out. So an interaction variable is just two variables multiplied by each other. We're going to do more of those today.
Wait, so we subtracted them there?
We added them, but one of them's negative, so.
Oh, okay, never mind.
Who asked the question? Oh, does that make sense? Then we did this 3 more times? 4 more times? Okay. 3? Yeah. Repetition. Practice makes perfect. Not again, because I don't think I ever explained it.
That shows up when you do the Excel, right?
Yeah, the outright. Yeah.
We don't need to know that.
Yeah, I was gonna say, you
I'm
really want-
good.
It's the probability of observing, it's a conditional probability. It's the probability of observing this value if the true value is 0. So 0 is good, meaning that if the true growth rate is 0, In other words, if the true slope of this, and that's what this coefficient is, if the true coefficient of this line, if the true slope of this line is 0, then what's the probability that we get a coefficient of 8%? The probability of that is 0. You don't need to know.
Okay, you know what, just scratch that question.
Yeah, yeah, that's why I kind of hesitated at first. You know, when you present at board meetings or whatever it is, there's, the boards are gonna be a lot like this class. You're gonna have some people that were engineering majors or engineers or math majors, and they're gonna know this stuff. They know this stuff and they always wanna show off that they know it. And then you've got people that were business majors, like this stuff is Greek to them. It shouldn't be, but it is in a lot of schools. Thankfully, John Stanton was smart enough to say, we need to do this stuff, so. Well, you're probably not thanking him right now, but he recognized the need for this stuff. And I'm still amazed that you don't learn this stuff in business school. How many were business majors? And this is all Greek, right? First time? Roughly? Yeah. This is what it is. But that's why we're here. Any other questions? Feeling better, feeling confident. I'm doing my best to slow this down and make sure we got this before we progress.
Can you see this?
This. That we're pretty comfortable with this, because it's about to get more fun.
Great.
I mean, it would help if we got our homework, like, and we knew how bad we did on it.
Yeah.
You know what I mean?
Just looking at it from here, pretty bad.
So,
I'm joking.
I mean, the one prior.
Oh, yeah, the one, yes, there.
You know, like, okay, wow, and we had thought I understood it, then I get homework back, and I'm like, okay, maybe I understood it well.
Well, yeah, the point is to not look back and push on forward.
And then you look back and find a little lower tricky.
Yeah, you'll figure that stuff out when you get the problem sets. Now, let's get back to what the heck we're talking about. What does this say about the movie Sideways? What's the whole point of this exercise?
The whole point of it is to see if sideways had an effect. So from this first graph, it appears that something happened because Merlot was growing, and now suddenly around the same time as we released this movie, now Merlot is not growing, it's kind of just flatlined.
So it looks like Sideways had a big effect on the growth of Merlot.
Possibly.
Well, yeah, based on this homework.
Based on only this first little analysis, we see a
Yeah.
correlation.
Yeah, we broke it down by price point to try to see, you know, where it was more effective and all those kinds of things.
Yeah.
But lots of things could have happened at about that same time. I mean, it didn't, but, you know, say the movie came out in September 10th, 2001, right? The next day is September 11th, 2001. And maybe people weren't having as much joyous occasions on September 11th as they were on September 10th. And we don't know that. We do know that the movie came out much later than that. But in other words, there could have been some other confounding event. The economy, right? We had the worst financial crisis since the Great Depression in 2008. We had a recession in 2002, if I remember correctly. So there could have been other things that are going on to explain some of this. Maybe it was the movie, but we want to be sure. And we probably don't want to, so we want to do what?
I can isolate, do people use like study and insurance a lot?
Yeah. Yeah. How would you do? I mean, what makes sense?
Could you look at other varietals, sorry, that's me. Hi. Could you maybe
Are you a
look at
ventriloquist or-
other varietals to see if they change? Because if it was something economic, it wouldn't just be Merlot
It
that
would
would be
affect all of them, yeah. So we wanted to look at something that shouldn't have been affected by the movie Sideways. We probably don't want to pick Pinot, right? Because in the movie, they praise Pinot and they dog Merlot, at least in the one scene. But we want to pick what we call a control group, right? A control group that shouldn't have been affected by what's called a treatment. And this really comes from the drug industry, right? So let's say I came up with a cure for the common cold. And my cure for the common cold is sniffing blue dry erase markers. I feel like I'm coming down with my cold. And I show that people that sniffed blue dry erase markers, which I've now patented, and I'm going to charge a whole lot of money like that guy that bought that drug patent, and raise the price from $13 to $750. I'm going to raise the price of this $1 pen to now $500 because it cures colds. And it gives a nice little buzz too. So I grab a sample bead. I have you all, assume you all have colds. I have you sniff the glue, and then we look at how we look at your progression over time. But what happens with colds over time?
They get better.
They get better. Yeah. So I don't want to attribute getting better to sniffing blue dry erase markers when in fact the cold would have run its course anyways, right? I want to do what? I want to get another random sample of people and that also have colds, but that didn't sniff blue dry erase markers. And we know you're both going to get better. We know you're both going to get better. But I want to see if they get better faster relative to this group, right? That's how we do drug trials. And that's what we want to do here. We want to pick a control group, and see if it reacts different to the treatment, and the treatment now is sideways, relative to the treatment group. And that's what we're going to do. And as you'll see, it's going to be awesome.
So like if we compare it to another varietal, and let's say the other varietal had similar results as Merlot, say you'd say it happened with both varietals, so then would you discount the claim that the movie had an effect?
Yeah.
What if that other varietal showed growth, but the Merlot showed death? Then you would say, well, maybe the movie had an effect.
Yeah, then the effect was even greater because, well, we'll see here. Yeah.
Couldn't it also mean that, I mean, if it was a, let's say Cabernet, for example, I mean, I know on the last one when we looked at Cabernet, it saw huge growth, but it was small case numbers.
Yeah.
Let's say it was large case numbers around the same as Merlot. Couldn't you say that the large increase in growth could offset the Merlot and cause Merlot to decrease? So necessarily seeing an increase, a continued increase in growth could cause the Merlot growth, because people are no longer buying Merlot, but are buying Cab instead.
Yeah. But you'd have to say, why are they no longer buying Merlot? And that's what we're trying to deduce. We're always trying to deduce cause and effect. we want to see if the movie caused an effect. If sniffing the dry erase marker caused us to get better quicker than those that didn't sniff the dry erase marker. So a lot of it has to do with the selection of the control, of the treatment, control and the treatment. When I did the Walmart study, I had to compare cities of similar size and demographics. So we have, not every city has a Walmart, or not every county, if I looked at county level data. Not every county had a Walmart. So I had to pick a county that had Walmarts and compare it to another county that I thought was size and demographically similar. So it all comes down to the selection of the control group. We know the treatment group. The treatment groups are the cities that had Walmart come in. But then we had to carefully select some control. And we'll look at kind of some measures of that. All right, so let's get back to this. Good question. And we're now experts in this simple before and after analysis. Let's kind of progress through comparing two groups, the treatment and control group. And here we're going to have a simple model, and we're going to add in a variable for a treatment group. 1 if you're in the treatment group, 0 if you're not, if you're in the control group. Then we're going to add a variable that identifies the difference in this time trend of the treatment group relative to the control group. And that's just going to be another interaction variable. It's going to be our dummy variable times our treatment variable times time. And there's our model. And let's just call the treatment variable treatment, and let's just call the interaction variable treatment times time. All right, what's next? Same model, it's the same model we had up a minute ago. And here is, what is this? This is our control group. And we start with the control group because it's easy. We zero out the treatment variable, right? For the control group, then treatment equals 0, and beta 3 goes away, and beta 2 goes away. Everything goes away, we're left with that. So when we zero out everything, we're left with the control group, and that's the growth rate of the control. And those are the, now we're really back to that first simple model, the homework that you guys haven't got back yet. There.
And there's no event at that point.
No, we're going to do this one step at a time. All right, now here's the treatment group. We rearrange the coefficients and we get that. We got a difference in intercepts and a difference in slopes. Now, if the treatment group and if the treatment had no effect, then what would be true? If the treatment had no effect, if sniffing the blue pen didn't help your cold, what would be true?
It's parallel?
Same slope.
And
Same slope and same coefficient.
you're right, same slope, but we would expect any difference in the two groups to be the same. In other words, remember beta 2 is the fact that I took the treatment. So if the treatment had no effect, beta 2 should be 0. And then beta 3 is the speed with which I was able to get rid of my cold. I got rid of it faster. But if the treatment had no effect, then beta 2 and beta 3 should be 0. And then those lines would basically be on top of each other, right?
So is this like they move in like, element the two trend lines and then index them and graph them against each other?
No,
Oh,
this is just two lines being the same,
okay.
meaning there's no difference in the treatment and the control. And we can see that because, right, just erase that, and what do we come up with? The control group one. And if there's no difference between the treatment and the control group, then the treatment had no effect. So this would be something more akin to, like I said, sniffing the blue dry erase marker. We're trying to see if one group behaved differently than the other. And as long as our two groups are the same, similar ages and all those kinds of things, race, gender, a lot goes into selecting proper control groups. Right? If my control group, right, I'm going to patent this. I want to make millions and millions of dollars off my cure for the common cold. And let's say that as I run this experiment, and for my control group, I go round up some cancer patients, chemotherapy, radiation, the whole 9 yards. If you're on chemo and radiation, a cold can do what? A cold can kill you. Exactly. Hey, people that sniffed my pen, none of those guys died. And they got well a lot quicker than the control group. Those people got, they had that cold for 6 months, 8 months. Some of them died. So it's not just a cure for the common cold, it could save your life. It's the kind of crap that goes on in drug trials. That's why the things get refereed. Double-blind treatment control groups. Same thing with research. Should be reproducible. Any questions here? And we can see the econometrics are basically the exact same thing as here, but instead of looking at the effect of an event, we're looking at two growth rates, two linear growth rates. But we still have treatment as a dummy variable, 0, 1, and we still have an interaction variable with the treatment and time to see if the slope is different. We just don't have a before and after, which we'll get to very, very shortly.
I'm just thinking, so like, let's say where it crosses the y-axis.
Mhm.
So the ln, like if Merlot sold 10,000 cases, but we're gonna look at Cabernet, which sold 20,000 cases. When you do the ln of those two numbers, it's a different ln, right? I can't think of what it would be right now.
It's a different intercept, yeah.
One might be like reduced from 10,000 down to 9, the other one go reduced from 20,000 down to like 14. So it's a different intercept. So would you say but then let's say they have the same slope. They have the exact same slope, but they're running parallel to each other, just from a different, one's high, one's low. Then do you say that they have the same slope, so there was no difference? You said there was no reaction or whatever?
Yeah, and beta 0 would probably be a difference in beta 0 would represent a difference in the control, the treatment group relative to the control. I'm sorry, beta 2 would represent a difference in the treatment group relative to the control.
And that difference being what, like the quantity of
Yeah,
observations?
probably quantity, something like that.
Okay.
In a drug trial, there would be some difference in demographically, maybe a different age or something.
So in our graphs this week for our homework, we're not seeing like where an event changed our slope. We should be seeing two separate lines if the treatment or control group were different. We should be seeing two completely.
And the ones you're handing in today?
No, next week.
But next week?
Like for our homework, we should
Yeah,
be seeing.
we'll get to that in a second. So we're gonna basically add now an event to this analysis. So we know how to do a treatment and control group. It's the same way we did before and after. So we know how to do it before and after. We know how to do a treatment and control group. We need to merge those two things and have a treatment and control group and then compare them before and after the treatment to try to see if the treatment had an effect. That's about it.
But you're keeping the population the same, in my mind. So you have patients, because I can understand that.
Okay.
That are two groups of people that you've offered a solution to.
Yeah.
The two groups of patients are the same. And now you're gonna add an event, but you're adding to an event to the two groups of patients that are the same. They're not different types of wines.
Yeah.
So I'm missing something, because in my mind, the drugs make sense, but the wines don't.
Well,
Because you don't have that control element. You have two separate somethings.
but you have this other something that shouldn't have been affected by the movie Sideways, and that's really the key part. So, for our purposes, the main thing that we're gonna look at is the after. It's not in this graph. It's really the after. But it's the after relative to a control group. So maybe when we finish this, it'll make more sense. And this is why we didn't do, this is why we just didn't compare two different wines to begin with. Because we want to see if the event had similar effects on something it shouldn't have had similar effects. If the movie Sideways had a negative effect on Merlot, then it should show that, but the movie Sideways shouldn't have had a negative effect on any other varietal, right? Because of the scene. Do we all know what we're talking about? Have we seen the movie?
Yeah.
No?
Until you might want to, because.
Well, it's, so in the movie, Paul Giamatti's character, he's a wine snob. And at one point in the movie, they're meeting with some girls, and he says, "I'm not drinking any fucking Merlot." And he says it really loud, he's really mad. Because he sees Merlot as for what?
Girls.
For girls or people that aren't wine connoisseurs. He's a wine connoisseur, he's a wine connoisseur, he knows all the distinctions about wine. He's not drinking any fucking Merlot, because that's for common people. You might as well be drinking out of a box. And in the wine industry, for wine producers, if you talk to them today, they say they're still recovering from the Sideways effect. So they believe it, which had a real effect. And we're just trying to quantify that. And the results don't look good. We see this. So we just need to see if this was caused by something else. So we're gonna look at a varietal that shouldn't have been affected. Yeah.
Just a quick question. What if like the demographic like died? Like, what if their only preference was Merlot?
Yeah.
You
And they happen to die in 2005.
Yeah, they died in 2005.
Yeah, and that would be fine. If we're looking at snapshots, I'd say that would be, yeah, and I'm looking at, but you're right, if let's say there was a plague of Merlot drinkers.
Yes.
And they just happen to die, that's a hard
You're
question.
lucky you're 2005.
That's a tough question, yeah. But what I did was, we'll talk about that in a little bit.
Did you look at all wine sales after that?
So I looked at all wine sales, I looked at different control groups. So let's get on to this and then we'll talk about the control group. And hopefully this won't be too rough. All right, so let's do this. Okay, so we know that beta 3 is the difference in the time trends, right? The difference in the time trends between the control group and the treatment group. All right. Now we're going to analyze before and after an event relative to a control group. So we're going to start with that previous model. Here's our before and after. So here's the model we just finished, having a homework on. This one. Right? So we're pretty comfortable with this one. Now we're gonna add the elements of the treatment and control group. But we know it's already gonna be almost the same. We're gonna have a dummy variable and an interaction. So we just need to see how exactly to put that. So let's add in a variable, a fourth variable, x4, that equals 1 if you're in the treatment group, and 0 if you're in the control group. So we're just adding a fourth variable. And then we did what? We added an interaction of the treatment variable in time, which is x1.
Our interactions are always multiplication.
Yes. It's always, yes. Two variables multiplied by each other. Okay. But now we have to add a variable that identifies the treatment after the event. So it's going to be the interaction variable. It's going to be another interaction variable. But it's going to be x4, which is the treatment group, times x2, which is after, the after variable. The dreaded triple interaction. Yes, you can have triple interactions. And it has a very, very specific meaning. Because it's the interaction of x4, which is the treatment group, x2, which is after, and x1, which is time. That is, it's going to be the change in the slope of the treatment group after the treatment.
Can you say that one more time?
I'm not sure. It's going to be the change in the slope of the treatment group after the treatment. Let me rip through this real quick. Not real quick. There's the model, and then I'm just going to change it. Let's call x4 treatment, like we did before. Let's call x5 the interaction of treatment times time. Let's call it treatment time. Let's call x6 the interaction of treatment and after, treatment after. Let's call the triple interaction what it is. It's treatment after time. Then we get that big old model.
Yeah. Yeah, I did. Paul said that he used to.
All right. Let's do one more thing. What is the control group, or what is the treatment group? Merlot. We think Merlot was affected by the event. So we get Merlot, then we got the interaction of Merlot in time, and then we got the interaction of Merlot in after, and then we got the interaction of Merlot after time. By the way, this methodology didn't exist before. Before I did. And we got that nice big equation. But remember, we're really generating two variables. generating two new variables. Compared to our last homework, we're comparing two new variables. We're generating two new variables, right? We're generating a treatment group. No, wait a minute. That's up. We're only creating one new variable, a treatment group. All the rest are what? Interactions. We're interacting the treatment group in time. We're interacting the treatment group with after. And then we've got the triple interaction of after time. Treatment group after time. One variable, and then we construct all these other interactions. All right, let's look at a graph. In a bit, let's look at a graph. All right, so let's look at the zero group, which is the control group, which is when our treatment variable Merlot equals 0. So it's the non-Merlot, Merlot equals 0. And let's look at the control group before the event. And that looks like what? That equation is what? Yeah, it's that. It's this homework that we did repeatedly. Now, let's look at the control group after the event. Right? This looks like what? What's that? It looks like the homework you're turning in today, right? In fact, it is the homework you're turning in. That's it. It's the same exact equation. We zero those things out. I'm sorry, we won those things out. I'm not sure if that's a proper word. All right? We collect the terms, and that's exactly what we've done for this. For the control group, the regression model boils down to the last homework and the homework you're turning in today. There's a method to the madness to try to feed you this one step at a time. Be glad you're not in my quantitative marketing class. That one, they get it all at once. Plus some. All right, any questions? So right now we're right back where we are today. The next thing to do is to look at the treatment group. That is when Merlot equals 1, when treatment equals 1. All right. For the treatment group,
No, we just did the treatment, right? Oh, never mind.
let's look at the treatment group before. If we're looking at the treatment group before, then anything with after is going to be 0. And all the after variables 0 out. So that's the equation for the treatment group before the treatment. I can move for glass of milk. And what do we do? Merlot is just a dummy, right? So those dummies are 1 because it is Merlot, the treatment group. And we end up with the intercept, we end up with this equation. And what can we see? If we were to, if the treatment group had the same slope as the control group before the treatment. And this is just logically, trying to keep track of all this stuff. If the treatment group had the same growth rate, same slope, before the treatment, what should be true? If the treatment group had the same slope as the control group before the treatment, what should be true?
The growth rate should be the same.
So what should be true? You're right, you're 100% right.
So it should be, right here.
Parallel?
Yeah.
True, but what should be true?
But the grades are the same.
So if the growth rates are the same before, what should be true in this equation? What'd you say?
Would be the same after?
Yeah, but how would that be reflected? So remember that the control group is LNY cases was beta 0 plus beta 1 time. See if that helps. If the control group and the treatment groups have the same growth rates before the treatment, what should be true?
So the slope has to be the same, and the beta 1 plus beta 5 be the same in the next one.
So how can beta 1 plus beta 5 be the same as beta 1?
If beta 5 is 0.
Exactly.
Which what?
0.
Is 0. In other words, if they have the same growth rate before, then beta 5 should be statistically indistinguishable from 0. It's just the pure algebra. And I mean, I hate to call it algebra, but we're not solving for anything. We're just saying, in order to make that equation equal to that equation, what has to be true? Beta 4 and beta 5 should be 0. More importantly, beta 5 would be 0 because beta 5 represents the growth rate. Does that make sense? And it really does help seeing this as opposed to a regression output. Because a regression output, you want to be able to look at a regression output and think in these terms, as opposed to, oh my God, this is a really big regression output. What the heck does it mean? If you can put things in these terms and write them down, you've got them in your notes. If you can just put things in the right place, you outreg it, you can calculate these growth rates pretty simply in Excel. Theoretically. All right. Let's now look at the treatment group. Oh, we are the treatment group, but we're looking at the treatment group after the event. So both Merlot and after are equal to 1. So we got the full model. This is the same as the full model up there, final model up there. Got the full model. Then we're going to one everything out. Whatever the heck that means. All right. Wherever there's Merlot and wherever there's after, we're going to replace those with the 1. You don't really need to replace them with the 1 because that's what you end up with. They're either constants or they're coefficients of time. Collect up all the constants, like we have been doing, and collect up all the coefficients of time, and we should come up with that. looking at the control group first. Why? Because everything, or a lot of things get zeroed out. So, the equation for the control group before the treatment is that. We saw that earlier. That's the intercept, and that's the slope. So beta 1, beta 0 represents the intercept for the control group before the treatment. Beta 1 represents the slope of the control group before the treatment. And really, it's always the coefficients of time, the growth rates that we're more concerned with. After the treatment, then the control group equation boils down to that, which again we derived or showed through, again, not algebra, we didn't solve for anything, we just collected terms. I'm not sure what that's called, mathematics, basic mathematics. Beta 3, we know, represents the difference in slopes of the control group after the treatment relative to before. So this is the last homework. We already did this. Right? This is nothing that we haven't done. Yeah.
So the treatment group is the one that's affected by the event,
Correct.
presumably.
Yeah.
So wouldn't we expect the control group line to be a
But-
straight line?
Possibly, but something else could happen too, so.
Okay, okay.
you know. So we're allowing for whatever, for all kinds of stuff. But you're right.
What's
The control group, what's that?
What's the control though?
What's the control group?
Yeah.
The control group shouldn't be affected by the event. They shouldn't. If they aren't, then beta 3 is going to be 0, and beta 3 will be 0. Oh, we're missing that intercept, which is down there. And beta 2 will be 0. So the control group shouldn't be affected by the event. Those that didn't take the drug shouldn't be affected by the drug. All right. So here's our simple before and after. All right, changing the time trend for the control group after the treatment is beta 3. Now here's the treatment group. There's the equation for the treatment group before the treatment. Where beta 4 represents the difference in slopes of the treatment group relative to the control group before the treatment. What's that?
Will you say that one more time?
I'll try. Beta 4 represents the difference in the slopes, the difference in the intercept of the treatment group before the treatment relative to the control group. This distance here. It's the difference in the intercepts before the treatment. It's the difference in the intercepts between the treatment and control groups before the treatment.